Symbol for natural numbers?
I was going to say base.
N.
Yeah, brilliant. Great start. What's the next bigger set? You know when you do the sets of numbers and one's a subset of the other and all that?
Base 2, base 10.
Huh?
Base 2, base 10.
Base 2, base.
Is it decimals or integers?
Integers big. So you get like -2 and stuff, that's integers.
Is that I, sir?
That's, no, integers,
Z?
yeah. Z, and sometimes they put the double Z like that. Yeah.
Numbers, you get R, Q.
The next one is fractions.
Fractions.
So fractions then, and recurring decimals and decimals you can write as a fraction. What's that called? No, you just want to go straight to real numbers.
I'm giving you one and you can keep
The rational numbers. Rational. A ratio of two numbers. Ratio, rational. And the letter is, what's the letter? No. Q.
Because R is real number. Yes, rational.
Q comes from, what's the Q from?
Question.
No.
Quotient?
Quotient, yes, quotient, yeah, Q from quotient.
That's so smart.
Okay, so, yeah. And then there's irrational numbers, of course.
Isn't that like 3 over 2?
Yeah, so rational and irrational are side by side. They don't overlap. Yeah. So
Integers fall into irrational, or is it its own thing?
these would fall into this. Yeah. Now irrational numbers. Can any of you give an example of an irrational number?
None.
No, like root 2.
Yeah, root 2 is a good one. Yeah, root 2. Root 2. That's irrational. So what's the definition of irrational then again?
Is it not a ratio of numbers?
Not a ratio of two numbers. Very good. Yeah. So you can't write it as a fraction.
It's not a rational number.
The symbol for irrational is actually kind of weird. It's like a not rational. No, you won't have to do that. No. You will see though in exam questions, and you've probably seen this already. You will see these symbols a lot. Usually this one comes up a lot, where you see that you could check your answer as an integer.
Wait, what's an integer?
Is that negative?
Positive or negative whole number.
No, it's just root 2.
Positive or negative whole number. So if you're not sure, yeah, this is all whole counting numbers. Okay, and then there's a really cool one, which I'm just putting as a side. A transcendental number.
Is it a Q with the thingy on top?
Yeah. It's like a little squiggle on top. Transcendental number, what is that?
We need to know it.
No, I just put it in for interesting. You're only going to learn exactly what you need to know and nothing more.
Is it like that, or is it like that?
Just a squiggle. There's no. We won't fight over it.
Anything above Q, irrational.
I beg your
Yeah. If there's something above a Q, yeah, we get it. Yeah, it could be a line, yeah. Okay. Transcendental is not imaginary, no. Oh, didn't spell it right. Transcendental. So good start. Transcendental is not imaginary. It's a special type of number. One way to explain a transcendental number is you cannot draw it. As in, you can draw root 2 pretty easily. If I walk 1 meter that way or draw exactly a 1 meter unit this way and do 90-degree angle and do 1 meter that way, how does that help me draw root 2? Yeah, the hypotenuse is exactly root 2. How do we know that?
There's 1 squared plus 1 squared.
Square root, yeah. So 1 squared plus 1 squared square root is root 2. So we can draw root 2. You cannot draw
So it can't be a line.
pi. You cannot draw pi. Like you cannot physically draw it through any way of geometry or algebra.
Pi is a transcendental.
Pi is a transcendental number. It cannot be drawn is one way.
So irrational falls into transcendental? No, because we just saw an irrational number being drawn.
An irrational number can be drawn. A transcendental is a type of irrational number that cannot be drawn.
Oh, so it's inside of irrational.
Yeah.
Okay.
Pi. E is another example. If you ever see E, 2.718 or so. E is used a lot in compound interest. If you see something compounding over time, it reaches a limit of E, which we'll get to at a different stage. Okay, so there's some numbers that we deal with. Now, all of these numbers are one thing, and Ryan, you said this about 20 times now. They're all real numbers.
Yeah. They exist.
They're all real. They all exist. Yeah, they're all real numbers. So that means we must be going somewhere else. We must be going into the unreal or the complex or the imaginary numbers. Okay, that's just the intro. Let's go back to quadratics before we go forward into complex. Can I remove this? This is just a side note. You'll never be asked to reproduce anything like that. All right, let's take a simple quadratic, x squared plus 5x plus 6. Let's do a few things with this. Let's look at, do you know sum and product of roots? Have you done that? Yeah. How do we get the, if you forget, we'll go through it again. So let's say the roots are alpha and beta. The sum of roots can be found using, do you remember this? Alpha plus beta and alpha beta. So this is the sum of the roots, and this is the product of the roots. They can be found without finding the roots. They can be found with the coefficients here. Yeah, one of them's.
It's in our book.
Yeah, I had to look through the book somewhere.
What?
It's like 1 over.
It's not 1 over.
Something over.
3 over A, is that what? No, that's different.
Oh, you're telling me the roots, yeah, and then you can get the sum from that. So the sum of the roots is going to be minus b over a,
Oh, it's minus.
and this is c over a.
Oh,
If you remember that.
B over A, but I don't remember C over A.
Yeah, so it uses the coefficients here. Because when you factorize a quadratic, you get the roots, and then they work back to finding these 5 and this 6, if you remember that from quadratics. When you do factorize it, which you can do here, x plus 2, x plus 3, isn't it? So you get the roots. Oh, x is minus 2 and x is minus 3. And when they are, I've done that wrong, isn't it?
No, that's right.
Is that right? Oh, yeah. Okay, x is minus 2. So you sum them. When I add these two together, what do I get? And when I multiply these two together,
Multiply is 6, add is minus
that's why I'm saying I've done it wrong. X plus 6, x plus 5, 2x, 3. Oh, yes, right. Okay. The product of the roots, the sum of the roots is minus 5, and the product of the roots is 6. Yep. Alpha plus beta.
Oh, yeah.
Yep. Does that mean?
Yeah, makes sense.
Yeah. Or you could have done minus 5 over 1. And what's the other one? C over A, 6 over 1. It's the same thing, okay? Okay, so the sum of those and product of those is that. Okay, that's a rejig. Let's do a different, look at a different function. Let's look, which is the one I have written down here. Oh yeah, x squared plus 2x plus 4. The sum of the roots, let's just go straight to it, minus b over a is minus 2, yeah? And the product of the roots, if we knew them, is 4. Yeah? Okay? Sarah, you good? Okay, so we got the sum and the product of the roots. Okay. If I were to sketch this, what would it look like? I want to sketch this. So I'm going to go to sketch it, I'm going to go to a little bit of completing the square.
Wait, the roots are 2, so 2 and 2. Oh my god.
So if I want to complete the square of this,
It's something, and then it's in brackets, and then on the outside, it's
okay, I'm going to help you out here.
all completed squares.
I feel like we're going to have to go over completing the square, maybe? Yeah, so add and divide by 2. We'll go over completing the square again. This is one way, so I've split up the 4 into 1 and 3, because I noticed that this is a perfect square. What's the perfect square here? X plus 1 squared plus 3. Are we happy with that?
Yeah.
That's this written just another way. How does this help us to sketch?
Gives us the vertices.
Well, it gives us the vertices, also a transformation. So it's transformed how many up? 3 up from what? So our base function, our parent one, is this one, isn't it? So this one has been transformed 3 up and 1 to the left, yeah, because the plus, yeah, it's like the opposite, yeah. Okay, so it doesn't look like that. This one looks like, and this would give the vertex, of course, as well. So what's the vertex? Negative 1, 3. Yeah, negative 1, 3. So it's going to be, let's say 3 is here, negative 1 is there. So it's around, sits up here somewhere. And the vertex is negative 1, 3. Very good. Okay, fantastic. What do you notice about that? There's no roots. There's no real roots yet. How did I get a sum and a product of roots if the roots do not exist?
Because it's complex.
Yeah, because, well, this is where it's going. Now, if I were to finish this and you were using your completing the square finish, and completing the square can be used to solve an equation, a quadratic equation. You know, when you want to get the roots of this one, you let it equal 0, and we did it down here. We didn't write this is equal to 0, and we finished it off equal. We got 2 roots. And this one, yeah, we can definitely see it goes through at -2, -3. This one, if I wanted to finish this, I could, I'm going to remove the sketch. I'm going to let it equal to 0 and find out what the roots would be. Same as over here. So I'd get x plus 1 squared is equal to -3.
Is it not -2 is -2? Root 3 minus 1, is it?
This one?
Yeah.
You sure?
If you factorize, it's just -2.
So if you that'd be x plus 2 squared, you're saying?
Oh, wait, no, that's x.
That'll give 4x4, yeah.
Yeah.
Yeah. So if I finish solving this, what's the next step to solving this?
Root 3 plus -1.
If I have a square on one side with the x, I have to square both sides, or square root both sides. So I get equals the square root of a negative number, which up until now you would say that's illegal, that's not possible. So you'd stop. But now we're not going to stop. We're going to introduce this concept of an imaginary number. I, yes. Yes.
I must have been
Guys, remember the equation a plus 5b, and then you do all that?
God, I think I must have missed like 60% of the final math. I was gone.
Well, if you haven't done it already, we're going to do it again. Yeah, and we're going to finish it properly. So this is not new to you, but it's kind of new.
I know what I, but we never really talked about it.
Oh, okay. All right.
Introduced,
All right. Yeah. All right. So you've done a bit of it. That's okay.
but we've done that.
Well, yeah, now we go over A to C over A, but I don't remember getting. I mean,
Sum and product roots is in the first unit. The first unit you should have done algebra. The first algebra.
So
unit.
some of us went to like Vietnam though, and we missed out. Like,
No,
I
we
was
got that.
like, oh, term one.
You
You think I remember from term 1 last year?
Okay. All right. Well, let's do what mathematicians did in about 1700 and go, okay, well, there is obviously an answer to the sum and product of roots, but this is illegal, so we have to have some way around it, and that is the concept of I. I is what? Yes, so I is the square root of -1. It's the base case of a complex number, I suppose. And any negative square root can be written now in terms of I, because with surds, if you have something like, you can split up a surd like this, but you can also split up the square root of -3 into root 3 times root -1. That is the same. That multiplies back. It's like you're expanding it. So this is now okay. I'll just write the same thing over here. It's not now okay. It's kind of a skip around. It's kind of what we want to continue with the maths because we know there's a solution somewhere, and yet usually we stop here. But now we're trying to link, so we find this sum and product again of roots. It has some roots. It's just not on the x-axis, on an imaginary axis. Okay, so this is not this anymore. This is, okay, I forgot plus and minus, of course, classic. This is plus or minus root 3i.
Is the I on the inside or the outside?
It's definitely outside.
It's lowercase too?
It's lowercase, yeah. It's definitely outside. Some people put it in front. It's the same. It's like 2x or 3x. And now I can finish that, and that's -1 plus or minus root 3i. And that is the roots of this equation. There are two roots. One is with the plus and one is with the minus. So minus 1 plus root 3i is one root, and minus 1 minus root 3i is another root. Okay. So if I multiply these together, what do I expect to get?
0. Wait, oh, that.
The product? What's that? This?
What are you multiplying?
If I multiply these two things together.
Aren't you supposed to get the
If I multiply it in a certain way, yes. If I multiply it like this, yes, yeah, minus 1 plus root 3i times x minus 1 plus.
Is it minus 1 minus 3i squared?
It is the 1, is
Oh,
it just
no.
negative 1?
I guess no, because it's a. Because it's multiple.
Okay, let's not multiply straight away. Let's add straight away. If I add these two together, what do I get?
Minus 1 minus 2.
Minus 1 plus root 3i plus minus 1 minus root 3i. So I've got the two roots, and I'm going to add them together.
Minus 1 plus minus 1 is minus 2.
Minus 1 plus minus 1 is minus 2, yes. What about this plus root 3i and minus root 3i? Yeah, they're just going to cancel out. So when I added them, when I summed them together, added them, what did I get? Negative 2. Which is the same as that. So it does work out. These are the correct roots. They're just imaginary roots, and they will fit this. It's the missing piece from when we got a negative square root to this. They're imaginary roots. They're not real roots. They're not along the x-axis. Okay, and if we did the product, this is a difficult one to multiply, so maybe at the end we'll multiply it. Yeah, Hisham?
Because minus 1 times minus 1 is.
Times, no. I said we'd do the sum first. I was doing the product, and I said that might be a bit complicated. We do the sum, so we're just adding them together, this plus this. Well, we get to the product in a second. It's going to be 4, yeah.
But like, I see how to do the product.
Yeah, we're going to do the product, yeah.
It's like you times the 3's together and they do the thing.
So when we were adding and subtracting, you kind of did it automatically. When you were adding these complex numbers, you added this bit to this bit, and this bit and this bit took care of itself. You added the real to the real and the complex to the complex. So each complex number has a real bit and an imaginary bit. So it looks something like a plus bi, something like that, or ib. The real bit and the imaginary